Yeah, so before we dig in to the main topic, I figured we'd cover a little bit about me. I am at Indiana University, and I was crazy enough to pursue something like this. I also realized that some of you may be working off last night a little bit, and so I have a lot to talk about, and since I only have 30 minutes to do it, we're going to hold questions, but also if you go to my website, sacrodeo.us, or you just go to this link, the presentation is already online, and I'm told that the link will be active on the Dyalog user meeting page after noon or something like that. So if some of the stuff sort of flies by because we got to go through it pretty quickly, you can read it in your own time offline on your phone or tablet later today and ask questions or bring those questions to the workshop if there's not enough time right now. So hopefully that will work. If not, let me know. And to frame this whole thing, for those of you not familiar with Co-dfns, is we're really trying to pursue high-performance APL, the classic problem of compiling APL, targeting the GPU, but my twist on it is I really want this to be as plug-and-play usable or as humanly usable as APL is in practice. So that's where I sort of draw my special line in the sand, is trying to get parallelism to be as accessible to the domain expert as it is to, people like me who spend an insane amount of time, as you'll see, on, do we lay out our bits this way or that way on the GPU? And then do we have to change it when we change CPUs? So a little bit of a recap from last year. So last year I was, the compiler was producing GPU code. It was sort of ready for people to start breaking it in more interesting ways than it had been broken before. And we asked everybody to send in their code, give it a try, see what happens. And we really were intending to start working on expanding the optimization, sort of expanding the runtime, what it could do, and work on improving the usability of the compiler moving forward for people to make use of it in their sort of future work. So where did that lead us? Led us down a big, giant gaping hole that is GPU programming. And basically what this means is we did get user code, yay. And so we've got a number of users. I'm going to sprinkle user stories throughout this talk. And we've been focusing primarily on what we need in terms of runtime performance and compiler optimizations to make certain user benchmarks fast, or make it easier to write those kind of benchmarks or write that kind of code and get it moving in the right direction for the compiler over the years. So a key focus in this past year, has been on getting really fast GPU implementations for certain things that are critical moving forward and making things work, and expanding out that runtime to handle some of the edge cases that really affect performance. And the good news is that we're actually seeing some pretty good numbers now relative to the dialog interpreter for some real user style code. And that's allowed me to get what I call this performance tipping point, which is, there's always this question of when we will be able to use the GPU in terms of whether or not your code will work, and whether or not the data you're working on will be beneficial, and whether you should even pursue this. And for me, the absolute bare minimum, if you have less than 100 megabytes of data that you're 1 megabyte of data that you're processing, probably more like 10 to 20 megabytes in a lot of typical cases, there's probably no chance that the GPU is going to provide any benefit to you. There's just way too little data. Really, you start to see those crazy GPU performance numbers when you get into the 100, 200 megabytes area, and then you really start to be able to see your time cut down as the data sizes get larger and larger. But if you've got above 1 to 5, 10 megabytes of data, you can probably see some performance benefits. How great they will be, I don't know, but that's sort of the tipping point of where you want to think in terms of how much data we have to process before the GPU becomes useful. So this has interesting implementations for bit vectors, and I've spent a lot of time on bit vectors this year because bit vectors are very space efficient, but they require some sort of computational heavy work to make them happen. And so you can't naively take bit vector algorithms and put them onto the GPU and expect anything to happen well. In fact, it stinks really badly. So a lot of what I've been doing is really playing with these bit vectors. We had to make some changes in the runtime to try to get bit vectors even sometimes just competitive with the CPU level code. Thanks, Roger. Because the CPU has certain primitives that are really nice, and the GPUs don't necessarily have that. So for bit vectors, your sizes are going to be larger, where you can start to see performance benefits, or you have to have really inconvenient shapes. So if you've got shapes that you just can't make power of 2 in the last axis of the column of a bit vector matrix or something like this, then the GPU might be able to actually get really good performance for you versus the CPU. But if you've just got a single vector and you're trying to do a sum reduction on a bit vector, we can probably do something there. I'm still working on it compared to 15.0. The answer would have been more positive in 14.1, but so there's still a lot of work to be done with bit vectors, but so it's a sort of a neck and neck race in terms of that because of how space efficient bit vectors are. Fortunately, there's still lots of wins to be had with that. So we've got big new shiny things to talk about. Lots of cool stuff. I've been hard at work trying to make things happen. Here's a brief summary, and you can see why we're going to run out of time. But just to do a quick overview in case I don't get to touch on all of this stuff, we've got a new caching API for keeping things onto the GPU, good for performance, essential for certain benchmarks. Some of the operators have been vastly improved, and I'm really excited about some of those. Those are really cool, so we're going to talk about those. We've been expanding out the runtime primitives, especially in those cases for common things that people are doing on benchmarks, big data that really makes a difference in terms of how fast something goes. And we've got better GPU implementations on a number of primitives. So we've been reworking the frameworks on some of the other things to make that faster. And DWA integration is a huge new thing that actually was driven by a non-member of the APL community wanting to play with the compiler and running into trouble. So I'll talk about that a little bit later as well. And so we have, well, actually, it's kind of exciting. So, or exciting for me, I don't know about you guys, but basically this APL guy, or non-APL guy, Neophyte, sent me an email saying, hey, well, I want to play with this compiler, it looks pretty cool, how do I do it? And I realized that he had never actually touched APL before. So he tried to get Dyalog, that worked okay. Then he got the compiler, that worked okay. Then nothing worked, that wasn't so great. Because we had this dependency on DWA, on the direct workspace asset. Yes?
I'm not sure people are familiar with DWA.
Oh, okay. So Dyalog has this very cool, is it secret? It's not secret, but it's, I guess, not widely used, where you can actually write foreign code that talks directly with the interpreter without a lot of the overheads of the quad NA interface in a certain conversion stuff. It's very cool, and it lets you work directly with dialog structures and interact with the interpreter's memory allocator, all sorts of things like that. And for a compiler guy trying to integrate with Dyalog, that's great, except that you have to talk to Dyalog, say, give me a copy of this. They have to send you a copy of it. You got to make sure it works on your compiler, and so forth and so on. And really, this guy was on a Mac, so he was already way off the beaten path in terms of what we were expecting. And so DWA really was not flying at all. So instead of that, the DWA features that I need have now been integrated into the compiler itself, so it's not an explicit dependency anymore. You don't need to talk to Dyalog and get DWA. It's already built into the system. It uses the DWA technology, but without you having to do anything, without any configuration. And so we stripped down the dependencies for running the compiler, and so now you can make it work. And because of this guy, we've also added preliminary Mac OS X support. Do not bring OS X laptops to the workshop on Thursday. You will be ignored. And in addition to this, we've got this new caching API. And this caching API came about because of another user who's trying to run some code, the Genokey code. And the problem is that as you're trying to convert code over, you have this copy overhead. So what happens is you can't always convert your entire program to dfunds and a closed namespace right away. So you focus on the hotspots, and you focus on what you need to convert. But sometimes those hotspots are located in different areas. And if those hotspots are located in different areas, you can get copy overhead because the normal invocation of the compiler will copy the data back into the interpreter after each hotspot. And then you've lost everything. It ruins your performance. So what we have is a caching API, which allows you to explicitly allocate or move a dialog array into the GPU and leave it there. And then you can pass it directly into Co-dfns compiled code and keep it on the GPU, and it won't be sent back to the interpreter until you explicitly say, now I want my code. So what this allows you to do is convert smaller pieces of your code incrementally into the compiler and avoid that copy overhead, and you get you get better performance. Now, of course, the end solution that you're going for is to convert as much of your code as possible so that the Co-dfns compiler can work with it, but that's not always practical in terms of what the compiler might support right now and what you can support in terms of programmer time for making that happen. So this allows you to continue to get intermediate speedups throughout this process without having to go whole hog into the compiler. And let's talk about high performance operators. So we've done the caching API, that's cool, DWA integration, that's cool, but operators are sort of the heart of making APL go, and we need these to go really fast. So we have another benchmark, and this benchmark makes heavy use of products, reductions, bit vectors, this sort of thing, and we needed something that would go really fast on that, and we did. So what we've done is the inner product and the reduction operators now are very fast on certain cases of the operation. They're fast in general, but for certain cases they're really, really fast. This is probably an area where Dyalog could spend a little more time in their interpreter if it was relevant, but we can see up to 300 to 400 times improvement, and that's 40,000% as opposed to the 400%. And you can see that even for relatively small sizes, you can't see, but the small sizes up there are relatively small arrays, like a 128 by 128 matrix, and these sort of sizes. So even at the small sizes for certain shapes of your arrays, you can get really good performance improvements. And we made use of this in one of our benchmarks to make something happen. So the result is we combined the row by row algorithm that Roger has talked about in previous Dyalog conferences, and we've played with that and then put it into the GPU, and we get some pretty good performance. Now, certain cases we're still sort of very neck and neck with the Dyalog interpreter, but otherwise in other cases we're doing quite well. And outer product and each. So these are now doing very well on primitive operations or certain operations that we optimize the context of to eliminate overheads and things like this. So these will work well. There's still some work to be done here in terms of user-defined functions, which I'm going to talk about later. Each also does this. We're using the new code generator for the each operation so that it will generate good code even for slightly less standard cases. But again, there's still few edge cases that we have to deal with here. And then we've been doing a lot on the mixed scalar primitive side of things to fix up how we handle bit vectors and how we handle non-scalar operations. So in 2015, we had some pretty good implementations of the scalar primitives. We've improved those a little bit and also have spent a lot of time optimizing how the mixed primitives on various pieces work. So this means that when we've got non-powers of 2 for bit vectors, we can actually do pretty well on the GPU relative to the interpreter. And here's an interesting one that we got. There's a group of eager, young, optimistic hackers who are interested in pursuing auditable cryptography and want to do things like replace Libra or OpenSSL with implementations that are faster and easier to audit. So they're looking at APL to do this, but they need something that will run fast. So what we've done is we've deviated a little bit from the traditional role implementations in that we tend to provide cryptographically appropriate roles, which is a feature you can get on Dyalog, but it uses some, it's not quite as reliable, or it doesn't quite meet, we're using the LibreSSL random number generation tools instead of pulling, say, directly from dev-random or something like this. So we get a little bit of extra pieces. So if you're into cryptography, this is good. If you're not, you don't care. We're looking at other roles in the future as well. Yeah, so they're actively working on this. I don't know how fast they're working on this, but they are pursuing it. So you might also see some high-performance big number libraries for APL in the future, things like that as well. And all of this sort of goes into the idea that we're moving into a new code generation framework, which is allowing us to do a lot more work with the shape and range information. So things that Roger's been harping on for a while, things like short range sizes, things like that. We're trying to integrate runtime analysis with the compiler analyses and make use of them in our code, which requires that our framework can handle that. So the compiler is progressively moving in that direction. Now, we've got enough time. I may spend the rest of the time on this. I may not. I don't know. Scan. You guys all know what scan is, right? Yeah? Yeah, okay. Turns out scan is very useful for a lot of things, and I will clarify that even more. On the GPU, scan is life. You must have scan. Scan is what allows you to do pretty much everything. I'm hard-pressed to think of any really non-trivial algorithm on the GPU that isn't one of these classic, easy-to-do procedural or rectangular algorithms. To do all the non-trivial stuff that looks sequential, but you can actually parallelize it, scan is what you need. And people like Guy Blalock have shown this for a long time. You have to have this stuff, and you have to have a good implementation of that. So I ran into this year, and I had to go spend a lot of time in scan. And so it's the single most important operation for things like sorting, reducing, filtering, replicating, key, groups, multisets, trees, databases, all of that requires scan at the lower level to make use of any of the existing literature on parallel GPU vectorized operations, or at least that I've found. If you've got another approach, let me hear about it. So I've put in a lot of effort into this. Unfortunately, a lot of the literature out there on scans are not written with the APL scan in mind. They're written with other very highly tweaked scans that are making a lot of assumptions that we can't always make in case. And one of the versions of this is what I call scientific computing quality code, which basically means they write a lot of code that runs really well on exactly one machine, and only one machine, because that's all they care about. They're being paid hundreds of thousands, millions of dollars to make it run on one machine, and that's it. And the problem with that is that the rest of us have to work very hard to use it on other machines. And I've encountered this a lot with scan. You've got, they make design decisions that really work well on their benchmarks and really don't work well if you have to produce production code. So this has been a bit of a struggle. And you can't really understand what you're doing with the GPUs until you understand the hierarchy. And so with the GPU on NVIDIA, you've got 3 levels of hierarchy. These warps, which are like these lockstep vectors, these blocks, which execute warps in parallel, and then these symmetric multiprocessing units, which execute blocks in parallel. So what you have is you have these 3 layers of parallelism, each with a different execution model and a different cost model, all being involved in your parallel execution, and you need to optimize at 3 different levels in order to make your code scale on a GPU. And there are design decisions you have to make to trade off a lot. There's a lot of trade-offs to make. So this diagram here is one of NVIDIA's classics, where your computation starts as a grid, and then you divide your grid up into these blocks, and these blocks are these single units that are each going to have some number of threads running in them, and the number of threads that you run have to be a multiple of 32, and each of those 32 elements is going to run into this lockstep little block, and at certain levels you can synchronize, at certain levels you can't. And then the GPUs are going to dispatch these blocks that you have onto their symmetric multiprocessing units, and they're going to run each of those in parallel, and you can think of the blocks almost as like heavyweight POSIX threads or something like that. And so this is how we do scan on the CPU. This is for a scan. It's a serial scan. We do one number, we add it to the next, keep going down. Now, obviously you can see that this isn't very efficient from a parallelism standpoint, because in order for each thread to do the computation for its number for which it's responsible, you have to wait on the thread prior to it. So people have invented tons of other versions of scan. Here's one. I believe this one's Brent Kung. This is an early one. This does reduction and then scans afterwards. So you can see how we start turning these computations into trees, and people have come up with a lot of these different things. We have a Kogi-Stone warp scan. This is one of the most popular ones. It's also one of the least computationally efficient, but it's really, really good on warps, because in lockstep, wasted computation isn't so bad. Memory access patterns is better. So this has nice memory access patterns. Unfortunately, if you can't control your synchronization correctly, then this doesn't become very good. So you've got something else. You can do a reduce then scan warp instead. You can do Sklanksky, which is communicationally efficient, but the access patterns are strided. So you're making trade-offs again, and you have to have barriers between certain points. And the list goes on and on. Now, at the block level, we can't just use that last one. That was just for a warp, 32 threads. Now we have to compose these 32 threads together, and they need to have synchronization, so you've got to have these barriers put in. So you combine something like, here, this is a Brent Kung scan, and then you combine it together with a scan, then propagate. So we do it, we reduce the results partly, and then we do this propagation fan at the end. Now, you don't have to necessarily understand how all these work, but this is just to give you an idea of the kind of algorithms that we're playing with. And here's, you've got Kogi warp scans for each warp, and then you do the Sklanksky. So you can compose these together and play with it. And sometimes you might even choose not to use all of your threads and choose to use only a few because of oversubscription on your GPU or any number of other reasons. And the problem is, well, first of all, which is the best? And the answer is all of them. Because you can't actually know in advance which is going to be the best one a priori. It's not like sorting, where really one or two algorithms has emerged as the best. One or two algorithms is the best on the benchmarks in the papers. And that's, in practice, not necessarily the best that you're dealing with, partly because of these global scan strategies. Because once you have these blocks, now you have to layer them all together again with a strategy for how to communicate between the blocks. And each block runs independent of one another. You can't communicate between them at all, except through global memory, which is more expensive. So what they do is they've played tricks where they implement old school synchronization wait loops across blocks to allow you to do all of this without having any global memory communication. But that doesn't work, because then you have to rely on having the GPU under your total control. You can freeze your machine if you try to do other work, all sorts of bad things. So what we've done is we've utilized a version of Sklanksky scan networks and reduced and scan global strategy, and have been able to achieve pretty reasonable performance. So to visualize this, basically, this is what Dyalog does, and this is what Co-dfns does. So we take this and we turn it into this, more or less. And that gives us our results. This is the diagram, you can look at this later, of how we actually put all of these together at the global GPU level. And all of this only scratches the surface of what you have to do. So we've got a pretty good scan, so now we're able to start tackling things like key, grade up, grade down, all of that, and we're able to achieve probably about 50 to 60% of what the performance people are getting in the papers and in the literature based on memory bandwidth, because scan is a memory-bound operation on the GPU. So in practice, what this means is that we're able to get about 25x performance improvement over scan on GPU right now. I'm looking to push that up into like the 40x, 40 times performance improvement. I think it's possible. So we'll see. And of course, as I said, we're running out of time. We might have to stop here, but I do want to talk a little bit about some of the new benchmarks that we received because this was user-submitted code. I'm happy to be playing with this. So we got a GenoKey benchmark, which gives us, which was motivating the results for the caching API. And this is a hard benchmark to compile all as a whole because it was using features that the compiler couldn't support yet. And by doing this, we were able to get some intermediate results and get about a 2 to 3x speed up on the original without having to necessarily convert the entire code base over. And if you look at the benchmarks repository, you can see that. And how do you pronounce that name? Gert? Yeah. So he was kind enough to let us work with this, and I'm very pleased with that. And of course, if you guys were here yesterday, you'd see the ANN networks, the artificial neural networks that are taking over the world. And with the benchmark that Romilly sent us, we were able to get about a 20x speed up on that on the GPU. And that's a complete, the compiler is completely controlling that compilation. We're not using the caching API or any of those other features. So that, I was pretty pleased with that as well. And that's making use of some of our reduction and inner product techniques and other tricks. So very quickly running out of time, so let's talk about how you actually use this just quickly. There is, you can study this in a little bit more detail, but for you to use this in your own code, basically what you're going to do is you're going to identify your hotspots, convert them to dfunds, put them in their own little namespace, and then compile that namespace and call into it as you need. And if you need to use the caching API because the copy overheads are ruining your performance, then you insert that caching API into the system and we'll let you sort of do that conversion incrementally. So now I feel pretty confident in being able to say we've got a pretty smooth way for you to transition into using the compiler by converting things into piecemeal, and it won't be so bad. So we've made a few changes that I want to cover in terms of, I know I'm moving through this really fast, but it's available online. You can read all of these a little bit later at your leisure. But chasing version 1 honestly wasn't working. Because it's never going to be feature complete because there's too many things that have to be done in terms of to make it really, oh, everything is done. It's not really there. So what I've been focusing on instead is we've moved to a fixed release schedule where we focus on the actual user programs. And the idea is to make it easy for you guys to track the progress of the compiler, monthly release cycles, every month comes out a new version of the compiler. On GitHub, you can easily submit your own benchmarks, things like that, and then you can, basically we're driving it by what code you guys submit to us to make things fast. So we submit us code, we make it fast, we repeat. And there's a file in the repository called limitations, which is a one-stop place for you to see sort of what features we haven't quite, known features that are missing from the compiler right now. And hopefully that limitations file will continue to shrink to 0 in the future. So GitHub is our main approach to working with this. There are 3 main ways for you to get into the compiler. You can submit issues of what does and doesn't work. That's the easiest. You can submit pull requests with your own test cases, and we'll put those in. Or you can submit a benchmark using the pull requests on the benchmarks repository and have that sent in, and we integrate that in with the benchmark suite, test it, get it to go fast, that kind of thing. And you can always email us if you don't want your code to be public. So some final thoughts. Really cutting it down to the wire. User-provided benchmarks are really, really important because that shows us what actually has to be done in order to get real performance. So submit us your code. Even if you are just playing with the ideas, submit some code and let us have fun with it. It doesn't have to be big. It can be big. Either way, we can play with it. We're on the fixed release schedule now, and especially send us code where you have these user-defined functions passed to operators inside of your hotspots. Because I'm looking at specifically optimizing some of those in the future because those turn out to be critical in certain areas. So if you've got any of those, send it. And I want to summarize that we actually had 5 user-driven improvements this year because of that. And so most of this new stuff has been driven by users saying, hey, I want this or not. And I'm basically out of time, so thank you. And don't forget Thursday's workshop where we can play with all of this in depth. So, yeah, thanks.